Yeah. Good evening. JWST+3, and I've got, what, 5 minutes? More? 5? Okay. 3.5 minutes, okay. Last year, I gave an update, JWST+2. So not surprisingly, this is basically an update on that. In other words, what's happened in the last year. So we all know that it was launched on Christmas Day 2021. Hence, it's now approximately 3 years old, if you take the launch date as day 0. It was sent up to L2, and it's currently sitting there 1 million miles above midnight on the Earth. Just a reminder of one of its jobs, as well as looking at the birth of stars and the birth of planets, it's also trying to look back in time to look at the very earliest stars and the earliest galaxies. So this is a timeline from the Big Bang to where we are now, and the redshift is a measure of how much the light from these objects has been stretched by the expansion of the universe. Very close objects don't have any stretch, so they correspond to a redshift of 0. Redshift is normally indicated by the letter Z. And as we go to greater and greater distances, that corresponds to the light being stretched more and more. And because of the great distance and the finite speed of light, that means we're looking further and further back in time. So a redshift of 1 corresponds to looking back when the universe was about 5 billion years old. Redshift of 4, it's a little less than 2 billion years old. But we think the first stars and the first galaxies were born right in that very early stage there. We're not sure exactly when, which is one of the reasons the James Webb was put up there. If we expand that region so we can see it a little more clearly, that first billion years or so, if we expand it out into a few 100 million years, the Hubble Space Telescope has already gone back to about a redshift of 10, so it's got down to about 500 million years after the Big Bang. And it's hoped that the James Webb Space Telescope, if it operates for a little while, will push that limit. So it will start to see stars and galaxies 500 or 400 or 300 million years after the Big Bang. We're not sure exactly where it's going to get to, but we hope it's going to be way down there on the left-hand side to catch the very earliest stars, the very first galaxies that were made after the Big Bang. That's the hope. So at the end of JWST+2, this time last year, I said that one of the things that James Webb has found is the most distant black hole. In addition to X-rays from the Chandra telescope, seeing X-rays from a source, and JWST seeing the galaxy in which that particular X-ray source existed, it was determined by looking at the spectra and hence the redshift of that particular galaxy, it was determined that this is a black hole at a redshift of 10. That puts it back to sort of the Hubble limit, if you like, of about 500 million years after the Big Bang. So that was the most remote black hole that had been seen to date. So let's have a look at a few things that have come out of the JWST this year, 2024. Back at the start of the year, it produced this rather nice mosaic reminding us that it doesn't only look at the most distant galaxies in the universe, it also takes a gander at some of the galaxies that are relatively close to us. And here's just a mosaic of a few of the candidates it's picked out, reminding us that it can see in the local galaxies, it can see an enormous amount of structure which allows us to understand more about galactic evolution, even though the more distant galaxies tell us about the birth of the universe. This came out some months later, a rather nice image of a so-called protostellar outflows. What this means is this is a star cluster being born, so there's a huge cloud of mainly hydrogen condensing and forming all the stars we can see in the image. This one was not only aesthetically rather nice, it was rather important because a lot of these stars that are being born have these so-called outflows, these areas of red, these jets that are coming out of stars that are being born. You can see some in the top left, and there's one down here as well. The reason this was an important image was because for the first time it's actually been verified that most of these jets in a star cluster actually line up. May not be too convincing from this image, but when it's looked at in detail, most of the jets coming out of the stars are lined up top left to bottom right in the image. Now, it was thought up to this point that when a gas cloud condenses and makes a whole load of stars, because that cloud was rotating, it would probably result in all of the stars in the cluster probably rotating, spinning in the same direction. This is the first time that it's been verified that that is indeed the case. Most of the jets are lined up, implying that most of the stars are spinning in the same direction, indicating that yes, that is how stars are born out of hydrogen clouds. They end up being born as a cluster and all spinning in the same direction. They might end up dispersing, but they are born all spinning in the same direction for a given birth of a given cluster. If we move on, this is still June 2024, but in this so-called JADES image, JWST Advanced Deep Extragalactic Survey, they love their acronyms, don't they? In this particular case, in this particular set of images, they've actually discovered a whole load of supernovae. You can't really see their supernova, but from the spectra, we know that these things are supernova. And all of these supernovae are at redshifts greater than z equals 2. That's significant because up till this point, up till the JWST, most supernovae that had been seen are much closer to home. So these are very distant supernovae. And what the JWST can do is measure the redshift of these supernovae to get an idea of their distance and measure how bright they are. Now we hope that supernovae are standard candles in the sense that when a star comes to the end of its life, this particular star, this particular type of supernova will produce a bright flash of light of a standard absolute brightness, and hence we can judge the distance to these objects and get an idea of how the expansion of the universe relates the distance of these objects to the redshift, which can be measured spectroscopically. If these are standard candles, if these supernovae always occur with the same standard brightness, then they are very useful for telling us about distances in the universe. But if James Webb takes a whole load of images like this and finds that actually at a same distance some supernovae are a little bit brighter than other supernovae, maybe they aren't standard candles. And if they aren't standard candles, then our whole idea of working out the scale of the universe starts to become suspect. So up till now it's been an assumption that supernovae are good standard candles. If JWST shows that they aren't, it has serious consequences for our understanding of the scale of the universe. So it'll be taking thousands and thousands of spectra such as these to try and figure out whether or not our thoughts so far about the scale of the universe are indeed correct. One of the most distant, at the moment, the most distant object as a single object that's been seen in the universe was indicated in June. It was actually Astronomy Picture of the Day in June 2024, and it's this smudge here. Not the whole of the smudge, no, it's this end of the smudge, because actually there are two galaxies here that just happen to be approximately in the same line of sight. So the rather redder galaxy indicated by the arrow, it's just as well the universe provides these arrows so we know what we should be looking for. But this particular galaxy, when James Webb determined the redshift of this galaxy, it turned out to be a redshift of 14, which is further than the Hubble has ever seen. So this is the most distant galaxy ever observed. It's actually about a little over 1,000 light years across. Bear in mind the Milky Way is 100,000 light years across. So a galaxy that's only 1,000 light years is tiny. Remember, we're looking back a long way in the universe, back to the days when galaxies were a lot smaller. Galaxies grow. They combine with each other, they merge, they collide, and they grow with time. So we're looking back to an era when galaxies were quite small. But even 1,000 light years means that we can tell that this isn't simply a black hole we're looking at. A black hole can't be 1,000 light years across. So this is not a black hole. We're looking actually at the stars and understanding whether we look at distant galaxies, are we seeing the light from stars or are we seeing the light from supermassive black holes? Understanding which they are makes a huge difference to how we understand the origin of black holes and the origin of galaxies. So this is one example where the most distant thing we can see, the light is coming from stars, not maybe a supermassive black hole at its center. That is in contrast to what I'm going to show in a couple of slides' time. So this particular one has taken us all the way back to z equals 14. So at the moment, the James Webb Space Telescope has pushed our understanding of the universe back to 300 million years after the Big Bang. It's hoped that we should be able to push it a little bit further, but it's clear that galaxies already existed at that point, so clearly stars already existed at that point, and it's still open question as to exactly when the first stars actually lit up. Was it 250, 200, 150 million years after the Big Bang? Hopefully, the next year or two or three, JWST will answer that question. As part of its second anniversary, first anniversary, it produced an image of Rho Ophiuchi. For its second anniversary of science output, it produced the penguin and the egg. Now, the right-hand side is presumably the penguin, and the little elliptical galaxy on the left is the egg. Now, some people say that looks nothing like a penguin. It looks more like a hummingbird. Well, you can make your own decision. But this is a spiral galaxy on the right and an elliptical galaxy on the left, which appear to have collided or at least interacted with each other. And the elliptical galaxy on the left has disrupted the spiral galaxy to the point where you can hardly see the spiral arms anymore. The spiral arms have been disrupted by the tidal interactions, and again, there's a whole new set of star formation, which is typical when galaxies interact with each other. This one was something like 2 years after, roughly 2 years after the very earliest images were released in the summer of 2022. Back then, perhaps you remember, there was a huge amount of hype and an awful lot of sensationalist headlines, especially in social media, saying the James Webb has seen galaxies that should not exist. The James Webb has seen galaxies that appear to be old, even right in the very early universe. Apparently, the universe is broken. There were lots of these headlines 2 years ago claiming that James Webb had seen impossible things. No, it hadn't. It's just rather premature to start analyzing data as soon as it comes off the presses. After a couple of years, they've carefully analyzed a lot of the data from some of these galaxies that are quite near and some of these galaxies that are quite far. And they have come to the conclusion that some of these very early galaxies that look quite bright are not as massive as they first thought. So in other words, trying to understand how a galaxy got to be so massive so early, well, actually, they weren't that massive so early. They were actually a lot less massive than they first thought, because the light they were looking at is not all coming from stars. A fair bit of it is coming from the supermassive black holes at the centers of these galaxies. So in other words, the question has shifted. The question is no longer, how did the galaxies grow to be so big so quickly? Because they didn't. The question is now, how did the black holes grow to be so big so quickly? It's a completely different astrophysical question. And so the idea of the universe is broken was simply, you're looking at the headlines far too early. Let the scientists do the analysis, and then they'll realize what the actual questions are and how they need to be addressed. This, one of the many images that JWST has taken, this one from September of this year. I show this one simply because it's a nice indication of the improvement, not the improvement of the JWST over the Hubble. They have very similar resolution, remember. The JWST, much bigger mirror, but works at much longer wavelengths. So the James Webb has got a very similar resolution to the Hubble, but the James Webb Space Telescope working in the infrared has a much bigger mirror than the previous infrared telescope, the Spitzer telescope. And if we compare this particular galaxy pair interacting here with the best that we could get out of the previous infrared telescope of the Spitzer, working with a much smaller mirror, we realize the improvement of the resolution. There's the Spitzer, so we knew this was an interesting interacting galaxy, but compared to the Spitzer, no surprise, the James Webb Space Telescope can do so much better, because technology moves on, and of course, James Webb, this enormous 18-segment hexagonal mirror rather than the rather small mirror of the Spitzer. Spitzer did fantastic pioneering work. The James Webb is now taking over. In September, again, 2024, just a few months ago, this so-called odd galaxy was seen. Why is it odd? Because it was determined, again, by looking at the spectra. You can't necessarily tell from the images, but the spectra that JWST produced showed that this galaxy seems to be glowing simply because there's lots of gas in there. The glowing from the gas seems to completely dominate compared to the glow of any stars that might be in this galaxy. So they're trying to understand how can it be this galaxy was perhaps made, or at least imaged, about 1 billion years after the Big Bang, so it's old by comparison with some other galaxies. But how can it be that this galaxy has got so much gas, the gas seems to be glowing far brighter than any of the stars? Well, it's thought that that might happen for very early stars, so-called population 3 stars. These are stars that were born from the primordial remnants of the Big Bang, the hydrogen and the helium, without any other heavy elements polluting the gas that formed these stars. So it's thought that maybe this would be consistent with a galaxy containing population 3 stars, except that, spectroscopically speaking, JWST says there are no population 3 stars in this galaxy, and yet the gas is shining far more brightly than the stars. And this is a bit of a conundrum. They've got to figure out, the scientists, the theorists, the astrophysicists have got to figure out how can we explain the existence of a galaxy like this that doesn't have population 3 stars. It's not made of stars that are only made of hydrogen and helium. There are heavy elements in there, and yet the stars don't shine as brightly as the gas does. Still not understood. This was an interacting pair of galaxies. This is one example of how Hubble and Webb work together. That's not unusual these days to have complementary images. The whitish part of the image is from Hubble. The reddish part of the image is from the Webb. In this particular case, these two galaxies aren't smashing into each other. One is sort of sliding behind the other, we think. So they are interacting, and because of the interaction, the tidal interaction of these two galaxies, again, whenever you get tidal interactions, you get new star formation. So they're not destroying each other, but they are stimulating new star formation. And again, the more of these sorts of galaxy interactions we measure or observe, then the more we understand how galaxies behave when they get close to each other. Might be useful for when we collide with Andromeda in 5 billion years' time, so it's useful to know these things. We're now up to December 2024. I thought this might be the last slide of this presentation. This is a couple of images of Vega. Vega, we know, has a dust disk. It's been known for quite a while from other telescopes that there is a dust disk around the star Vega. Vega, as you well know, is a very bright star, magnitude 0 star, whereas a dust disk around it will be very faint. So it's a real challenge to block out the light from the star and reveal the very faint dust around it. Hubble did its best to block out the star. Unfortunately, it produced quite a lot of these artifacts, which is the result, an optical artifact of trying to blank out a very bright star. There were other stars in the background as well. But essentially, Hubble didn't see any planets. Is that because it can't see planets very well, or because they're not there? Webb comes along and does the same job, somewhat better, because it's a larger mirror and a slightly better technology. And what does Webb see? Well, Webb is sensitive to slightly larger particles. Hubble would be sensitive to particles that are about a micron or so in size. Webb would be sensitive to particles that are a little bit bigger than that, perhaps smaller than a grain of sand. And yet, again, Webb says, well, there's sort of nothing there. There's a little bit of a variation in density as you get away from the star, but there's no indication of any clumping. There's no indication that any planets are trying to form in this star system. We've looked at other systems. You know that Kepler and many other spacecraft have seen thousands upon thousands of solar systems around other stars. We know planets are very common. Even Earth-like planets are quite common, and yet some stars do not make planets, apparently. Even though we think Vega has had long enough to make planets, it doesn't seem to want to do so. So one big question for planetary scientists is, why do some stars like to make planets and some stars don't? The more stars we look at that don't have planets, the better we understand planet formation in the first place. So I thought that might be the last slide, until I realized that, James Webb science releases keep on coming, despite the fact that I knew this talk was coming. And so at the end of November, they released this from the Sombrero Galaxy. For those of you who like the Sombrero Galaxy in visible light, perhaps you don't like this representation. But if you compare it with the Hubble, this infrared image shows a very clear disk of the galaxy and a very clear, very bright nucleus. And if I remind you what the Hubble sees when it looks at the galaxy, you see It's a reminder of just how dusty this particular galaxy is. You can see the dust ring simply from the absorption of light around the edge, around the equator, around the rim, if you like. And it's obvious that you cannot see really the far side of this particular galaxy. And yet, if you look with the Webb, you see the far side almost as clearly as you see the near side. It's a reminder that the infrared light can cut through a lot of the very dusty environments. Now, we know that the supermassive black hole at the center of the Sombrero galaxy is one of the biggest we know. It's something like 10 billion solar masses. The one in the center of our galaxy is 4 million. So this supermassive black hole at the center is at least 1,000 times bigger than the supermassive black hole that we have in our galaxy. And yet it doesn't seem to be that active. It is not eating voraciously all the matter around it. It is not producing humongous amounts of energy, which, for instance, quasars do. This particular supermassive black hole, despite the fact that it's absolutely enormous, is basically not eating voraciously. It's just having a bit of a snack on some of the material that's falling in. So it is producing some energy. It is producing some jets from this supermassive black hole. But we can get a better view of it with the James Webb, and so that will be analyzed, that will be studied more in months and years to come to get a better understanding of what happens when a black hole doesn't feed very actively and still produces jets via a mechanism that we really still do not fully understand. I thought, again, that was going to be the last slide of this evening until in December they came up with another one. This was released literally just a few days ago. And this is the Firefly Sparkle galaxy. You can see that they are now naming galaxies after characters in My Little Pony episodes, by the sounds of it. So they saw something interesting. It was being imaged by this galaxy cluster. A very distant galaxy was being imaged and hence distorted, because all galaxy lensing will produce distortions. So this particular galaxy was quite interesting. It has a couple of companions. The actual galaxy itself is about the same size as the Milky Way was at the same time. Again, we're going back to the rather early universe when the Milky Way was much smaller, and this galaxy is only a few thousand or so light years in diameter. These companions, these satellites 1 and 2, are only thousands of light years away. 6,000 in one case, 42,000 in the other. But remember, the size of the Milky Way now is 100,000 light years. So these things are closer to the galaxy than the diameter of the Milky Way as it stands now. But at the time, back in the early universe, this was the sort of typical separation of galaxies. This was interesting because it doesn't appear to be uniformly illuminated. It seems to be very blobby. It is quite definitely a collection of star clusters. This does not appear, even when you take into account the distortion from galactic lensing, this galaxy does not appear to be a central bulge and spiral or possibly non-spiral arms. It doesn't seem to be flattened into a disk. It doesn't seem to have a central bulge. This galaxy is so young, the star clusters in it haven't yet had time to sort of settle down and produce what we would understand as a typical canonical galaxy. If we take that stretch of galaxy and say, what would it have looked like if we didn't distort it by this gravitational lensing? Well, it's difficult to tell exactly what it would look like, but an artist's impression of what that galaxy might have looked like without the distortion is something like that. It is quite definitely not an elliptical galaxy. It is quite definitely not a central bulge and a flat disk. It appears to be a collection of very bright star clusters and a background smudge of other stars. So again, trying to understand why a galaxy should start its life like that, and perhaps we don't have the luxury of watching it, but maybe galaxies start off like this and eventually settle down into the sort of galactic structures that we tend to see in the universe around us. Again, it's one of these things, a lot of open questions, a lot more study of systems like this to try and understand why you have such a peculiar collection of stars like that. So it's not exactly a Christmas tree, but I think that's a good place to finish with a Christmas talk, and I wish everybody a very Merry Christmas.